Welcome to this video, which is submitted by the team of UIC Andrew Lab for the 2022 IEEE AP-S Student Design Contest. This is Yuzhu Ouyang, and other of our team members include Zhilu Ye, Mingye Yang, and Yi Chongren. High-gain source electrically small antennas have gained much attention in recent years due to their compact structures, high directivity, and efficiency. However, the reported high-gain source antennas are mostly realized with complex three-dimensional structures, which greatly restrict their applications in wearable Internet of Things devices and systems. To solve this problem, we herein present a wearable high-gain dipole antenna with a planar, single substrate configuration. It operates at 2.4 GHz industrial, scientific, and medical band with desired radiation characteristics. We will apply this wearable high-gain dipole antenna in an electrocardiogram sensing system, ECG, which measures the electrical activity and rhythm of the heart, would be one of the most representative IoT-based health applications. Traditionally, ECG monitoring requires wires connection with the test equipment and the human body, and it is performed in the clinics with the help of medical staff. Now, with our wireless ECG sensing system, the measured ECG signals are visualized in a smartphone monitor in real time, so that patients are able to monitor their heart in a prolonged and timely manner. Let us first introduce the characteristics of our high-gain dipole antenna, which consists of two near-field resonant parasitic elements, the magnetic capacitively loaded loop element laying on the top side, and the electric Egyptian X dipole element on the bottom side. There is a short coax-fed dipole right close to the CLL to excite the NFRP elements. The electric and magnetic NFRP elements have almost equal radiation intensity but orthogonal polarizations, which makes the antenna achieve a broadside cardioid radiation pattern. The entire structure of the antenna is electrically small, with Ka equals to 0.85, and low profile, with its length being around 0.22 wavelength. It's built on a single Roger 5880 substrate with a thickness of 0.508 mm, so our antenna can be ultra-thin and flexible, which are not possible with the traditional high-gain source antennas. Our measurements match the simulation results very well, showing that the antenna can radiate at 2.412 GHz with a negative 10 dB bandwidth of 34 MHz. At operating frequency, our high-gain dipole antenna has a realized gain of 2.78 dB relative to isotropic, directivity of 3.68 dB, and half power beam width of 155 degrees. The radiation efficiency is 78.4%, quite decent for such an ultra-thin, low-profile antenna. Let us see a recorded video for the experimental measurements of the reflection coefficient of the antenna.
Here's our Huygens dipole antenna under the measurement using a vector network analyzer. From the screen we could see its operating frequency is 2.4 GHz. The thickness of substrate of our antenna is about 0.5 mm, which is very thin and very flexible, so we can twist it or bend it in this way. And after that, its operating frequency would not change a lot, and we can observe from the screen. So it could still be used for transmitting the information.
Next, we implement the designed high-gain source antenna in the ECG monitoring system, which is made by an analog ECG front-end, a Bluetooth module, and a battery. The ECG front-end collects electrical signals from the human body and produce clean ECG waveforms with the assist of amplifier and low-pass filters. The ECG waveforms then go through an AC-DC converter and become this digital data ready for transmission. The Bluetooth system clipped with our high-gain dipole antenna can communicate with the portable device, such as a mobile phone, and transmit the measured ECG signal to the portable receiver. So with this ECG sensing system, we are able to visualize the real-time ECG signals on a mobile phone monitor. We notice that the entire system can be realized with a printed circuit board technology, which is low cost and easy to fabricate.
Here we use commercial ECG testing electrodes in our system. This is the entire system. In the future, the size of the system can be further reduced by integrating the antenna and the ECG module in a single flexible board. And to better show the great mobility of patient using this wireless ECG monitoring system, we assume one of our group member is the patient whose ECG information needs to be monitored, and another one is the doctor using a mobile device to monitor this ECG signal. It can be seen that the ECG information has been successfully transmitted to the mobile device, and then the patient can walk around following his will, and when he stops moving, the ECG information can still be robustly acquired by the mobile device. Additionally, the doctor can also have more flexibility while detecting the ECG information of the patient, like this. He doesn't need to set up complicated equipment for the ECG measurement anymore. Next, as for the patient himself, he can attach the system to his outwearing and also download the app on his mobile device. And in this way, he can obtain his own ECG information at any time, anywhere when he wants to. He can do his own things without any restrictions like the traditional ECG measurement setup requires.
With this ECG sensing system, we can wirelessly monitor the ECG signals, which provide information about the heart rate and rhythm, and show if there is evidence of various heart disorders such as arrhythmia and heart attack. From this zoom-in figure, our measured ECG signals can clearly show the detail of this sinus rhythm of a human heart. Besides ECG monitoring, our wearable high-gain dipole antenna may also be integrated in many IoT-based applications, including smart healthcare systems, telemedicine networks, and portable wireless sensor. This will be our future work. Thank you for watching.